Momentum conservation is one of those powerful laws of physics that helps us solve problems. Momentum and energy are two that we use together a lot. We can't always use energy to get completely through a problem. We can't always use momentum to get completely through the problem. But between the two of them, we can get through some very complicated problems and solve them. Let's take a look at where momentum conservation comes from. It's a combination of Newton's third law that says when two objects interact with each other, they exert equal and opposite forces on each other. And the fact that if our system is isolated, if we have no external forces on our system, then the sum of all the forces has to be zero because of Newton's third law. The only forces on our system are internal forces if we have no external forces. And all the internal forces have equal and opposite counterparts because of Newton's third law. So we know the sum of the forces on the system will be zero. And because of that, you can very quickly come up with the rate of change with respect to time of this quantity, mv, for all the objects in our system, has to be zero. It does not change in time. That means that this quantity is constant. So there's something special about this quantity. There's something special about m times v summed up over the entire system. So we're going to give this a special name. We're going to call that momentum. We use the symbol p, lowercase p. I don't know why we use a p for momentum, but we do. And that equals the mass times the velocity. Momentum is a vector quantity. It points in the same direction as the object's velocity. And it has units, kilograms, meters per second. And I always joke around with my students that we get tired of writing certain units. We get tired when we write F equals ma. We get tired of writing kilogram meters per second squared all the time. So we call that quantity of units, we call that a Newton. We just write newtons after that. And we have lots of things in physics. We get tired of writing all the different combinations of units, so we give it a special unit like the Newton. In this case, we never get tired of writing kilogram meters per second squared for some reason. We don't have any special unit for momentum. Okay, let's take a look at a quick example of when we would use this. I'll go into more details about different situations in the next video. But let's look at some simple examples. Let's say we have a cart 1, cart 2, and let's make cart 2 initially at rest and cart 1 initially moving to the right with some velocity. How about 2 meters per second? And let's make both of these carts the same mass. How about half a kilogram? What's going to happen? Cart 1 is going to collide with cart 2, and they're going to stick together, form one object. And they're going to move with some speed. I'm going to call that v final. We want to know what is v final. You might think you can use energy to solve this problem. You cannot. When objects deform, when two objects become one, when one object becomes two, like a firecracker exploding as it travels through the air, or when two objects become one, like these carts on this track, we know for certain that the mechanical energy is not the same before and after. In this case, the objects stick together, they probably heat up, sound is given off, energy is converted into types that we can't account for. The mechanical energy before and after this collision is not the same, so we cannot use energy to get through there. That's why we're learning about momentum. The momentum initial has to equal the momentum at the end. Because this is an isolated system, it's on a frictionless track or they're on wheels. We've got a nice isolated system here. We can use momentum conservation. Since this is a vector quantity, I'll want to define a positive direction. I'll pick to the right as my positive direction. Initially, I've got two objects in my system. I'm going to have to look at object 1's initial momentum and object 2's initial momentum and add them up. That's my initial momentum for the system. And at the end, I only have one thing moving, so I'm just going to call that P1 plus 2. They've joined together, they're one object now. So the momentum of object 1 is just its mass times its velocity. The momentum of object 2, its mass times its velocity. And the mass of the combined system at the end times its velocity. Now let me put in some numbers. The masses are both 0.5 kilograms. The velocity of object 1 is in the positive direction, 2 meters per second. The velocity of object 2 is 0. What do we end up with for V final? We get 2 times a half is 1. V final is 1 meter per second, and it's positive, so that means it's moving to the right. Let's take another simple example. Same carts on a similar track. Let's have the carts moving toward each other this time. Let's have our carts stick together. So at the end we have one big cart, and we're trying to find V final. And why don't we keep the masses the same? So again, we have two objects becoming one. We know for certain that we cannot use mechanical energy to get through this problem. If we had one object blowing up, becoming multiple objects, we know for certain we cannot use mechanical energy to get through it. But just because the objects bounce off of each other, like let's say we were analyzing somebody shooting pool, billiard, balls on the billiard table bouncing off each other, we still may not be able to use mechanical energy. Sometimes we can, and sometimes we can't. I'll talk about that more in the next video. Let's get back to this problem. Two carts coming toward each other and sticking together. So what are we going to use? Momentum. Anytime you have collisions, you should be thinking momentum. That's our special tool for getting through a collision. Initial momentum equals final momentum. Initially, we have two objects, so we'll add up the momentum each one has initially. And at the end, we only have one. Let's put some numbers in. 0.5 kilograms. V1 is moving in the positive direction. I guess I should define the positive direction. I'm dealing with vector quantities. It's moving in the positive direction at 2 meters per second. M2 is also a half a kilogram, and it's moving in the negative direction at 3 meters per second. At the end, we have half a kilogram plus half a kilogram. And V final is what we are looking for. 1 minus 1.5 equals V final. So negative 0.5 meters per second is V final. The direction is in the negative direction. That means it is to the left. And that makes sense. If we look at these, if M1 and M2 both have the same mass, and M2 is going faster than M1, it's going to win in this collision, and the combined system at the end will be moving to the left. Picture two football players, both the same size, running towards each other. One of them's running faster. What happens when they try to tackle each other? The one that's running faster is going to win. He's going to knock the other guy back, if they're both the same mass. If they're different masses, well, we have to figure out what happens. Let me take a minute just to do one more example, because objects don't always stick together. Let's say we have two carts, 1 and 2. We can have them moving toward each other. Afterwards, we have cart 1 moving in this direction. Let's say it's going at 1 meter per second. And we want to know what is V2 doing at the end. Momentum conservation, because this is a collision. Now, what you have to do is account for every object in your system. I have two objects in my system initially, so I have two momentum terms on the left side of my equation. I have two objects in my system at the end this time. In the previous examples, I only had one object in my system at the end because they had combined together to form one. Now they don't do that. They bounce off each other. I have two objects after the collision, so I have two terms on the right side of my equation for my momentum. Let's call to the right positive and put some numbers in here. So this is going to be 0.5 kilograms times a positive 2 meters per second. That's the initial momentum of cart 1. The initial momentum of cart 2, 0.5 kilograms times a negative 3 meters per second. That's going to equal the initial momentum, the final momentum of cart 1 minus 1 is its velocity. We have to solve for V2 final. Let's see what we get. We get a 1 minus 1.5 is equal to negative 0.5 plus 0.5 V2 final. So we bring the 0.5 to the other side and we get 0. So V2 final is 0. V2 comes to rest in this case if the carts bounced off each other the way I described here. I'm just making up numbers. It may not physically be able to do something like this. But if cart 1 and cart 2 were coming towards each other with these velocities, and cart 1 bounced back with the velocity of 1 meter per second, that means cart 2 would come to rest. In the next video, we'll look at different types of collisions and when we can and cannot use momentum.